Yep, thank you for introduction. My name is Hansung Kim from University of Surrey in the UK, and then today I'm gonna present my paper about immersive spatial audio reproduction for VR and AR using room acoustic modeling from 360 images. So it's a combination of computer vision and audio researches. So we all know that human perception relies on both mainly on audio and visual information. And some researches show that spatial and temporal synchronization of sound with visual information improve the sense of presence in VR and AR environment. However, the problem is that to reproduce some kind of a real environment into VR environment, it is really hard to recognize the acoustic properties of that environment, the space. Actually, the best way to reproduce the acoustic of the space is measuring room impulse response, but sometimes it is a bit difficult according to applications. Because to measure this kind of room impulse response, we have to set up some microphones and audio source, and then have to record it in this space. And another problem is that even though we record and measure it, actually that information is valid only for that location. So if the sound source or listener are moving or geometry is changing, then we have to measure it again for that kind of a specific point. So it is quite difficult to generate that one. And another problem is that even though we can reproduce some sound, some spatial audio in that space, still it is hard to know if that is good enough or not. So the way to evaluate it is another issue. So there are several issues, like coherency should be quite important, like audio-visual information should be synchronized and well-matched. And here I also introduced two different concepts for evaluations, like plausibility and authenticity to evaluate it. So plausibility is, it depends more on internal reference. So even though you don't know the real sound, if it sounds like that, then we can say, okay, that is plausible. Okay, it sounds like that. And that's enough. It can be enough. For example, in VR application, you don't know the real sound, the real environment. But if it sounds like that, if I'm there, as if I'm there, then that should be fine. But another way to measure or evaluate it is authenticity. It's more rely on external reference. So we know the ground truth, real sound, and then it's measuring how close the reproduced sound is to the real sound. So maybe in AR applications, this authenticity might be a bit more important because we can still listen to the real sound from real environment, and the virtual sound should be augmented on it, so they should be remapped to the real sound. So here, I want to introduce our system to reproduce them. It's quite a simple and practical system to estimate the room acoustics for reproduction of spatial audio using quite a simple, small 360 cameras. So we don't use any audio equipment to measure the sound, but just we use only vision sensors for that. Here we try to reconstruct some approximated room geometry and then understand the scene and then estimate the materials and then sound properties, and then try to render the sound in the scene. And here, this one is based on kind of simple assumption that human audio perception is not really sensitive enough to recognize the differences of sound from the change of geometrical details. So we have very approximate geometry, but still, even though geometry slightly changes or they don't have really details, but the sound effect in the scene, the difference, we cannot really recognize it. They're kind of a subtle differences. So this is the overview of our pipeline. So we capture the scene with two 360 cameras, vertically aligned one. And then the pipeline split into two different components. One is depth estimation from two cameras to get 3D information of the scene. And the second part is a semantic object segmentation from the image to recognize what they are and what kind of object in the scene. And then we combine those kind of results into the 3D room layout reconstruction. So we get the whole room layout and then rough location and size of object in the scene with their object labels. And we assign acoustic materials on those kind of individual objects. And finally, we generate a VR scene with the spatial audio in the scene. So this is capture system. So it's simply just we put two 360 cameras, which is quite cheap. Actually, we use this Ricoh theater camera, which is just only around the $200 each, so it's quite cheap. And we aligned vertically to capture vertical stereo. There are several advantages, like in-depth estimation, and also it produces less occlusion between cameras because they don't really see each other in important region in the side, but it's just upside down. And from that kind of two photos captured from two 360 cameras, we measure the depth, estimate the depth in the scene using spherical stereogeometry. So here, now this is another advantage, is that we don't really need a camera calibration for those kind of 360 camera if they are vertically aligned very well. Then if we know the correspondence point in two camera images, and if you know the distance, and then we can directly calculate real depth from the camera to 3D point with that kind of simple equation. So we can quite simply get the depth of the scene, though there are some unmatched points, but that kind of sparse depth map is enough to get approximated geometry. And on the other hand, we do semantic segmentation, object segmentation. So we use deep learning-based SegNet architecture developed by Cambridge. Here, if we can get some materials directly from the image, then it might well be better to produce acoustics. But problem is that actually material detection and recognition is much more difficult than object recognition. So here we just simply recognize the object, what they are, and then map the materials into those kind of object labels to make it simple and then more accurate. So here, so we categorize 14 categories of object in our research, and we mapped that kind of acoustic material properties with absorption coefficient and scattering coefficient into each object. Finally, we generated 3D room by cuboid fitting and labeling from the segmentation result and depth estimate result. So details are in the paper, but I won't go for details for that. And then we export that result into OBJ format for 3D geometry and JSON file for scene and acoustic information. And we import that kind of information from the Unity platform and then generate a special sound using Google Version's audio package. But we can also use a Steam audio package. Actually, it's just selectable. But we use the Google Version's audio for this implementation here. And for experiment, we tested in this kind of pipeline to several different environments from different sides of the room, and there's different objects in the scene. So some are quite a small meeting room, and there's more like a living room style, and we also have quite a big hall, like this studio hall. So we applied that for 4 different sets. And in computational load overall, for geometry reconstruction, we processed it on CPU, and it took around 5 minutes for geometry reconstruction for just one scene, I mean a pair of 360 images. And then for semantic segmentation, it can be run in parallel in pipeline on GPU, and then it took around 3 minutes running that SegNet and composition and decomposition of that. And this is a rough evaluation of a room layer reconstruction, I mean the room size. So that is ground truth, real room size, and the estimated from the captured images. And you can see that there are some kind of big errors there, yeah, like 27%, because this this ULC in this one, you can see quite a big window and big mirrors in the scene. So actually, it failed in getting some right location of walls. So that's the reason that it has quite big errors. So it is kind of limitation of this approach, vision-based approach. And from that, we try some kind of a more objective evaluation of reproduced sound related to authenticity. So we measured ground truth room impulse response in that same environment. And we also estimated the virtual room impulse response from reconstructed room by placing virtual sound source and virtual microphone. So we get 2 different room impulse response for the same set, and then evaluated into 2 factors. First one is early decay time for early reflections, and the RT60 for evaluate the late reverberation. And we also set just noticeable differences, J and D, according to the references, and then see how close they are and how to the ground truth. And then we can see that maybe you don't really need to care this kind of diamond ones, but maybe just circle ones. Diamond ones are result without object in the scene, just only with the room boundaries. And the circle ones are the result from estimating room impulse response. You can see that they are quite close to the ground truth. As I told you, for this kind of usability level one, it is very far because the location of the walls are quite wrong there in estimation. And in reverb, RT60, they are also quite close, but this studio hall has a bit big error because actually in actual studio hall, it is a hall like this, but actually they have some big panels on the ceiling and walls to absorb some sound. But actually when we estimate the materials, we just model them with just a flat panel of that. So it has more reverb than real one because our system could not recognize that kind of panels to observe the sound. That's why that has a bit more reverb there. Right. Here's some audio rendering, but when I tested it, I found that it doesn't really work on PowerPoint. Yeah, okay, so I will just play the video directly. Yeah. Right. So this is the sound rendering result. So first one is with the ground truth room impulse response, and second one show you will be the estimated room impulse response. So you can listen to sound, the difference of sound. And this one is estimated one. Yeah, estimated one has a slightly more reverb.
I just saw Jim near the new archaeological museum. I just saw Jim near the new archaeological museum.
Yeah, in Studio Hall you can.
I just saw Jim near the new archaeological museum. I just saw Jim near the new archaeological museum.
Yeah, you can hear that a bit more reverb in this kind of Studio Hall because of these kind of panels. So in ground truth room impulse response, it has a bit less reverb due to these kind of panels. And the next one is more interactive rendering of the sound. So here there will be three different audios. First one is just without any acoustic effect. And second one is with estimated geometry with object, and third one is just empty room. So here, actually, this is a binaural rendering, but unfortunately, you cannot listen to binaural rendering with this speaker system. But hope you can just feel some kind of a directional feeling of direction and also reverb together.
Museum. I just saw Jim near the new archaeological museum. I just saw Jim near the new archaeological museum. I just saw Jim near the new archaeological museum. I just saw Jim near the new archaeological museum. I just saw Jim near the new archaeological museum. I just saw Jim near the new archaeological museum. I just saw Jim near the new archaeological museum. I just saw Jim near the new archaeological museum. I just saw Jim near the new archaeological museum.
Yeah, actually, yeah, you could listen even some reverb because of this room. So maybe, I'm not sure, it may be slightly difficult to see the differences. Maybe, if you want, you can come and then I can listen with some headphone demo. And final one is some VR applications. Here, the user is interactively just navigate with the VR headset, and you can see on the screen, you can see what he is looking at, and then the sound is actually, we exported the sound to the speaker. So, and I just recorded with my mobile phone, so sound is quite noisy, but you can see what the user can see and listen. Okay, just let me go back to the presentation. Yep, so let me just summarize my presentation. So here we propose a vision-based 3D structure and acoustic property estimation system, and we try to reproduce some plausible spatial audio for VR and AI environment, and we implemented it on VR system. But there are still a lot of things to do because it's very initial work for this target. And so most of all, we need more like a robust material detection, because we just categorize only 14 different categories, but they are not enough to reproduce the right sound from that. We are also planning some subjective evaluation of plausibility in VR reproduction. And finally, we also need to investigate the perception of VR environment with and without visual cue, because normally it is quite well known that if we both have audio and visual cues dominate the perception. So we just want to investigate how much they affect each other. So there might be some topics we want to do. That's the end of my talk. Thank you very much. Okay, yeah. So it is really based on visual features to estimate the room geometry. So if I look at that point from two different cameras, and then we measure the distance from the difference between two images captured for that one. But if there's a mirror, actually visual feature on it is reflected from somewhere. So if you look at them from two different cameras, actually the depth point is not on the surface of mirror, but actually the distance in the real object reflected on the mirror. So actually it makes you really confused. And if there's quite a big window, then we can look through. The window itself is quite transparent. So actually the visual feature is taken from the real point through the real visual point behind the mirror. So the depth estimation is absolutely wrong. So there is a kind of limitation of a vision-based system. So in that case, we are also thinking about the combining different modalities to get it. Like we already tried using both visual and audio sensors, because audio reflection is really happen on the surface. So we get the distance from that. If we have some sound source and then recording from the first reflection, and then we can get the surface point from there. So we can just rely on both different modalities. So we are thinking about some other like depth sensors or audio sensors or some laser scan. Yeah, we are just trying to get that kind of things. And also we can also use some kind of deep learning to learn, okay, that kind of things should be a mirror, that should be window, and then we get some surface on there, maybe using deep learning by training. So there may be that kind of approaches to sort it out. Let's take our speaker one last time. Thank you.